This is the second part of the momentum overview we're looking at. We had some technical difficulties at the end of the first one, so we had to cut out. What we got to was the idea of the momentum equation for fluid mechanics. We saw that it was a complex partial differential equation that was nonlinear and would be impossible to solve analytically, and so we need computers to solve them. But what we would like to have to build intuition about the flow field are more simple algebraic expressions. I'm going to work towards that. The idea is we make some assumptions, and these allow us to simplify those equations. First, we're working along a streamline. Number two, the flow is inviscid, and that's valid for most of the flow fields we looked at. We look at the viscous effects will be confined to a very thin layer near the boundary. And finally, the flow is steady. So if we look at a point in the flow, like right here, the value of the velocity there will be the same and is independent of time. So any quantity that is a time derivative, we can simply cross out. The result of all this is we end up with a relation that looks like this: dp equals negative rho v dv. This is known as Euler's rule, Euler's equation. Euler has a lot of different equations, so you have to be cautious about which is what is what. This is Euler's equation. It's still nonlinear. You can see effectively you have a v squared in here, but it relates changes in pressure, dp, the differential change in pressure, to changes in velocity, dv. So pressure and velocity are negatively related, we see from right here. Is a very, very important fundamental equation, very powerful. Essentially, this governs steady, inviscid flow in the flow field. And so an option sometimes in CFD solvers is to ignore viscosity. Since it's confined to a small boundary layer anyway, you can get decent idea of the pressure field without it for high Reynolds number flows, as long as the flow is not separating. And that will give you, and Euler's formula is essentially what is, Euler's equation is essentially what is solved. If we add one more assumption, which is that the flow is incompressible. And again, what this means, generally speaking, is that the density doesn't change along a streamline, which we wrote as d rho dt equals 0. But in the book, we consider a more general case, where actually I guess less general case, that rho equals a constant everywhere. That's how the book considers incompressible. Simply constant density everywhere. If we add that in, then we get, we can derive from this, this expression here, we have dp equals negative rho v dv, where rho is a constant everywhere. We can integrate both sides here, from v1 to v2, from p1 to p2, and we get p2 minus p1 equals 1/2 rho v1 squared minus 1/2 rho v2 squared. We can sort this out to be p2 plus 1/2 rho v2 squared equals p1 plus 1/2 rho v1 squared. Or we can write this as p plus 1/2 rho v squared equals some kind of constant along a streamline. So if we have a parcel moving along a streamline, as it goes along, its pressure and velocity can be changing, but the relationship between them must always hold this simple relationship, an algebraic relationship. And you can see how pressure and velocity feed off of each other. If the pressure goes up, the velocity must go down. The velocity goes up, the pressure must go down in order to keep this a constant here. Pretty amazing. So that's known as Bernoulli's principle. People call this Bernoulli's equation. Now what we disregarded here, now this is really a trade-off of the kinetic energy and pressure work. This is not written in energy units, but you can think of it that way. Kinetic energy and pressure work. If we put P over rho, we would get there. This doesn't include changes in potential energy. So you may have seen another form of this, which includes the important effects of potential energy. P plus 1/2 rho v squared plus rho gz equals a constant. I'll put k prime here because this would be a different constant. This takes into account changes in potential energy. For the flow fields we're going to look at in this class, and I'm trying to think if there are any exceptions, I don't think so, the trade-offs in these two will absolutely dominate any changes in potential energy that may occur from some rise and fall of a parcel. For example, going up and over a wing, going up and around an engine. The changes in these terms are so large compared to this that we will essentially ignore this. Now, there's certainly problems where potential energy is important. Think about a dam break or any problems from hydraulics. It's the dominant term, or one of the dominant terms. Another form of this equation you may see is just this equation written a little differently. I'm trying to remember. I think they write it like this: P over rho g plus v squared over 2g. So I'm just dividing the whole equation by rho g plus z equals another constant. I call it k prime prime. This is the way the civil engineers look at Bernoulli's equation. The units are height or head. They talk about head differences. In all these equations, you really have pressure work, head work, and you have trading off with the kinetic energy of the fluid. In our case, we are going to ignore these potential energy effects, and we will always think of it this way: P plus 1/2 rho v squared equals a constant. It's important to recall that what went into this. Again, you have four assumptions. You have this is along a streamline. It's constant along its streamline. Another streamline might have a different constant. 2, that the flow is inviscid. There are no inviscid effects, no viscous effects. Number 3, it is steady. There is an unsteady Bernoulli equation, but we'll ignore that. It is a steady flow. There's no time variation, and the last one is that is incompressible. We will look later, as I mentioned in the continuity lecture, the compressibility could be related to the Mach number via the speed of sound. And so incompressible for us, for the most part, is going to imply that the Mach number is less than about 0.3. This is not a hard, fast rule. This is just a rule of thumb, I should say. Mach number is less than 0.3 in the flow field of interest, then we can, and it's steady, and it's inviscid, and we're working along streamlines, and all these things are true, and that those horrendous momentum equations can be boiled down to this: a trade-off between pressure and velocity. So we're going to work through some problems, quite a few problems actually, between class and homework, using this and invoking continuity to come up with calculations of forces and trying to better understand flow fields. Quite a bit in class we'll be talking about discharges of things from engines or rocket nozzles. For example, flow out of this rocket nozzle. This is a horrendous rocket nozzle, but flow out of here, right, to make this thing propel. What do we know about the pressure at the exit? If you're not given the pressure at the exit, then you may assume P at the exit is equal to P atmospheric. For most of these kind of devices, that is going to be true. If you pop a balloon, if you basically if you burst any kind of device, the air pressure at the exit is going to be at atmospheric or very close to it. Otherwise, what happens is, if you think about the streamlines coming out of this thing, so there's the air moving out of this rocket. If the pressure here is different than the pressure here, then that implies a force. If it's higher pressure here on the outside than on the inside, it'll tend to bend the streamline in. So again, this is you can think of this as the edge of a control volume, and there's a net pressure force acting on that control volume, and it tends to deform it. It will deform it, in this case, if the pressure is higher on the outside than it is inside the plume. And so unless you have converging or diverging streamlines, which we'll recover quite quickly, then that implies if they come out straight, which they essentially will, that the pressure, there's no pressure differential between the exhaust and the outside, meaning the pressure of the exhaust is the pressure of the outside, meaning the pressure of the exhaust is atmospheric or very close to it. So if you're not given the number, I always say it's safe to assume you at least start with atmospheric, unless something doesn't make sense or there's something else going on. But so that's one thing. It is something that's a little bit non-intuitive, but it's important to think about. We'll analyze a jet engine in class where we'll see that it's not quite atmospheric, but it's pretty close. And the second is this idea of force due to momentum. Again, our flux force, our fluxes of momentum, we have rho u times u dot n dA integrated over the control volume. If this is our control volume, this rocket right here, the only place you have a flux is at the exit of that rocket. You take the same integral. If u is normal, if the velocity is coming up perpendicular to that face, then u dot n is, oops, sorry about that, then u dot n is just u. There are no other components of the flow. V and W are 0. And so this thing boils down to just rho u, the exit velocity, you call it ue, rho e, times ue again, times the ae. So it's just rho e ue squared ae. You can see here, so we'll think of this, there's two ways to think about this. It's essentially a force. It's a thrust force acting on the rocket. The way we wrote the momentum equations, we had the rate of change plus the flux of momentum equals the sum of forces. But these were pressure and viscous forces. This flux is essentially, we can think of it as a force. Flow momentum acting on this control volume. You can see that it goes as the square of that velocity. It's quite sensitive to the exit velocity. So if you want a big force coming out of that rocket, for example, it's really important to somehow get yourself a big UE. And there'll be and we'll look at rocket nozzle design and see how essentially we can accelerate the flow up to that UE. You see here when I drew even the simple rocket, it seems to go through a narrowing before it expands, and maybe this looks like a rocket you may have seen before, a jet engine on a rocket on the back of the shuttle. Might look something like this. Why does it seem to narrow before it expands again? And we'll look at that. This comes down to the nature of supersonic flow, but the point is to get yourself a nice big UE for big thrust force. We'll go through some examples in class, but again, the key thing from this momentum is the idea is you start with Newton's second law, you apply it to a fluid, you come up with a very complex equation. That's a momentum equation for fluid mechanics, which accounts for the rate of change of momentum within the control volume, the fluxes of momentum through the surface, and the forces. And again, it's a vector equation, so you really have three momentum equations in 3D. You have an x momentum dealing with the x direction momentum, or rho times u. You have a y momentum dealing with rho times v, and you have a w momentum, or vertical momentum equation, for rho times w. If we make those assumptions of flow along a streamline, inviscid flow, and steady flow, we can boil it down to what's called the Euler's equation, where you can see a clear relationship between pressure and velocity. Even in that relation, you can see that pressure is negative related, didn't mean to make an equal sign there, is negative related to changes in velocity. This is Euler's equation. Again, this is for a compressible general fluid. As long as it is inviscid and steady and along a streamline. Then if we make that constant density assumption, rho equals constant, we end up with Bernoulli's equation. This is, again, comes out of the momentum equation. We're working along a streamline, and we find along that streamline, P plus 1/2 rho V squared is equal to a constant. So as this parcel of fluid goes along, changes in rho and V at different places are going to trade off via this relationship, provided there's no viscous forces acting. It's incompressible, so we're not heating the fluid, and we have, and it is steady in the sense that this parcel's moving, but if we look at one particular location at a time, the flow through there will always be the same. So this will be very important. We'll look at flow over an airfoil, for example, and we'll see how it accelerates here, and then the process of accelerating, the faster velocity means lower pressure, and then it'll tend to slow down here. And this will lead us to have lower pressure on the top surface, particularly near the leading edge, than on average than on the bottom. We'll create a net force in the vertical, and that net force we will see is lift.